This is problem 6-52E. It is on page 317. Water enters an ice machine at 55 degrees Fahrenheit and leaves as ice at 25 degrees Fahrenheit. Now understand that when your author gives you this information, he's assuming the water comes in the liquid phase. Okay. All right. If the coefficient of performance of the ice machine is 2.4 during this operation, determine the required power input for an ice production rate of 28 pounds per hour. And he gives us some nice information. He says 169 BTUs of energy needs to be removed from each pound of water at 55 degrees to turn it into ice at 25 degrees. So let's write down what we've been given. This is 6-52E. So here's the ice machine. As far as we're concerned, it's just a black box. We're not concerned about exactly how it works. Water comes in at what I will call state 1 at a temperature of 55 degrees Fahrenheit. Rate 28 pounds per hour come in. The water has to leave at 25 degrees Fahrenheit as ice. It's still water, but now it's in a different phase. So this is the liquid phase here. Okay, I'll call this state 2. Write a decent 2. Okay. So we'll have to put work into this to make it happen. And of course we'll have to extract heat from the ice to make this happen. That makes sense, right? I mean, ice doesn't have as much energy as the water does. So we need to pull energy out of the water to make this happen. Okay. In fact, you can see from this, since this flow over here has less energy than this flow, you can see that this flow of energy is going to be larger than this flow, right? Because there's some extra energy going this way, being carried in by the water. All right. Now, like I said, your author has given us some really good information because the change in energy of the water as it flows through is 169 BTUs per pound mass. So each pound that comes through here has to lose a certain amount of energy. So let's calculate how much energy loss that is. Well, now we know that's a heat flow, right? And it's going to be a heat flow rate because we have a mass flow rate. So if we multiply the mass flow rate of the water times the specific energy change of the water, that would be 28 pound mass per hour multiplied by 169 BTUs per pound mass. Okay, so that tells us how many BTUs per hour we have to pull out of the water. Well, if you multiply that out, you'll find that this is, doesn't look correct. Oh, that's because that's a comma, not a point. 4,732 BTUs per hour. That's how much energy we have to take out of the water every hour. Now, this is a heat flow. Is this Q dot H? Let's put these in rate form instead, okay? So, flow rate. Since we have a flow rate of mass, let's talk about the flow rate of energy. Is this Q dot H? How many people want to say yes? How many people want to say no? Wow, no confidence. Oh my goodness, your 220 professor was awful. Oh, wait a second. What's going on here? Well, let's look at it in terms of energy flows. Okay, let me use red for energy flow. All the work will have to, that's not a very good red pen. All the work has to end up as thermal energy. Does that make sense? Okay, we don't want to put this work into the water and let it come out over here, right? It would be at a higher temperature. That doesn't make sense. So ultimately, oh, that's no better. What do you know? Try green. Green will be energy. Good enough. There we go. Okay. So all of the work is transformed into thermal energy. But energy has to come out of the ice as well and add to that stream. In fact, this is the Q dot we just calculated. Okay? But this is the sum of those two. Let me draw it another way for you. Basically what's going on here is we have a refrigeration system we must put work into in order to pump thermal energy from a low temperature reservoir to a high temperature reservoir. Put dots on everything. So this Q dot we just calculated is Q dot L. Because really the water is serving as the thermal energy reservoir. Now, that doesn't sound right because thermal energy reservoirs are not supposed to change their temperature, right? That's true, but what we're doing is we're just letting the water flow through. So the water over here doesn't change its temperature, the water over here doesn't change its temperature. So in a way, it's still the same thing. We could just let water keep flowing and it would essentially operate as the thermal energy reservoir. In other words, that's where the thermal energy is coming from. Does that make sense? So anyway, look at an energy balance around this thing. This is just what we had before, right? The net work is equal to Q dot H minus Q dot L. It's just an energy balance. And it makes sense, right? It's an energy balance around this. It's already all it really is. Heat flows in, work flows in, they come out as heat. That's all it says. Nothing more difficult than that. Now the question is, how much net work is required, right? That's what we're supposed to calculate. In fact, there's one more piece of information I didn't write down. The coefficient of performance of the refrigerator is 2.4. Okay. So what is the coefficient of performance? What is that thing really?
It's the ratio of how much you get,
Desired
desired over given.
over required. Desired over required. Okay, good. What were you going to say? Right, it is defined by the heat sinks, and so you're saying, better yet, let's say it this way, it's defined by your purpose. Is your purpose to heat up the air in the room? Probably this is in a restaurant or something. No, of course not. Your purpose is to cool down the ice, right? So this had better be a Q dot L over W dot, right? Notice we don't have to calculate the high temperature heat flow. We could, but we don't have to. In fact, we'll do it in a minute, but that's not what's being asked for. So let's go ahead. Tell you what, let's work with this. We don't need this bit anymore. Let's just write Q dot L there now that we know what that is. Notice that if we want to calculate the power requirement, it would simply be Q dot L over 2.4. Just rearrange it algebraically, right? Just these two just change places. Okay. So that's 4,732 BTUs per hour divided by 2.4 will tell us the required work flow rate. And when I did that, I got 1,972 BTUs per hour. Now, if you go and you try to specify a heat pump in BTUs per hour of work, you can't, right? You need to specify it in kilowatts or horsepower or something like that. And so when you convert this to kilowatts, in the interest of time, I'll just write it down. This is the same thing as 0.58 kilowatts of power, or so. That had to round off a bit. Okay, so this is over half a kilowatt refrigerator. Now, the other part I wanted to work with you that I haven't worked on my solution is the amount of heat flow into the local environment. So Q dot H would be equal to, from this equation, the net power output plus the heat input. Okay? And of course, these are all in rate forms. So anyway, so the net work input is 1972 BTUs per hour. And the heat flow from the ice, we calculated that was 4,732 BTUs per hour. So grab your calculators, please, and just add those two numbers together. Let's see what you get. In fact, we'll continue with a few calculations around this. Some other things we can talk about.
Six 6704.
6704 BTUs per hour. Okay. Have I told you guys what a ton of refrigeration means? Remember that?
We discussed it, if I recall correctly.
Okay. Well, since we're talking about freezing water, this would be somewhat appropriate. This,
Energy required to freeze liquid water to ice?
right, that's right. Now, what's interesting is that, and the water has to be at the freezing point before and after the phase change, okay? And the normal number, if you look in the back of your book and you look up a ton of refrigeration, you'll see how much it is. Go do it if you would. Just tell me what it is.
200 BTUs per minute.
Okay, and BTUs per hour it's?
60, so 1,200.
I think it should be 12,000
12,000, yeah.
BTUs per hour, I think, if I
Yeah.
remember right. So anyway, that's the amount of refrigeration capacity you would have to have in order to freeze 1 ton of water in 24 hours. Okay, that's the way that's calculated. And the flow rate ends up being 18,000 BTUs per hour. So let that operate for 24 hours, so 24 times 18,000. That's how much energy you have to remove. Go ahead and calculate it if you would. I've never thought to calculate how much energy do you have to pull out of literally 1 ton of water to get it to go from 32 degrees water, or liquid, to 32 degrees ice, solid. So what is 24 times 18,000, or 12,000?
288,000.
288,000, okay. So you have to pull 288,000 BTUs out of a ton of water if you want to freeze it. Now, if it's at a temperature above 32, like this was, well then that's even more energy you have to pull out of it. So, anyway, where was I going with this? Oh, where I was going is that a heat pump is also specified based on its ton capacity. It's this idea, right? So its ability to heat a space is based on how many BTUs per hour it can move. And if it can move 12,000 BTUs per hour, it's a 1-ton heat pump, okay? Now, what's interesting about this is that if this ice machine is in a restaurant, let's say, and it's cold outside, then this is helping to take the heat load, right? Because this water is going to come in from the tap, right? So we get to put energy from the tap, thermal energy, into the restaurant. Well, that's a good thing, right? That's less heating that has to happen in the wintertime. In the summertime, this is a problem, because now our air conditioner has to not only remove the leakage in, but it has to remove this too, right? And that's a bad thing. In fact, this idea is used in, what are they called? Heat pump water heaters, I think is what they're called. I don't know their actual names. But basically, you can get these water heaters nowadays that are a lot more expensive than a regular water heater. They basically just have a chiller unit on top of it. And what it does is it chills the air around, uses the thermal energy it pulls out of the air, and puts it into the water. Now that's actually more efficient from a standpoint of your electric bill, because now you don't have to, you're not just taking in electricity and converting it all to heat. Instead of you're using it to scavenge some heat and put both of them into the hot water, which is a good thing. Well, at least it's a good thing in the wintertime if the thing's in your house. It's a bad thing in the summertime, right? No, I'm sorry, I got that backwards. It's a bad thing in the wintertime, but it's a good thing in the summertime because it's going to cool your home. Right, and so what they recommend you do is that you actually sit this out in your garage instead, so that it's more of a balance. You're sinking and sourcing from the local atmosphere instead of from your home. So anyway, but what I was going to mention is, notice this is about half of a ton, right? So this ice machine is accounting for about a half a ton of refrigerator, or heat pump usage, essentially. Okay? Now this might give you an idea. Well, wait a second. That's pretty cheap. So couldn't I bring in water from the tap, suck out all the energy from it that I could, figure out a way then to take that ice and toss it outside and heat my home in the wintertime? Well, you could. In fact, at one point I had students do some calculations to say, well, wait a second, how practical would this be? Let's look at your water bill and see how much water you'd have to pay for. I understand this is a terrible environmental idea, right? The idea is to use less water, not more. Okay, I understand that. But if it would work, how much would it take? Are we talking a gallon? You know, are we talking tens of thousands of gallons? How big is this? Well, it turned out it wasn't practical for multiple reasons. Number one, it required a whole lot of water. Number two, that water would cost a whole lot. Okay, so
And what about the power to run the ice machine?
well, it's less though. The power to run the ice machine is actually less. You are getting some free energy.
A little bit,
And, well, quite a bit, actually. You could actually get quite a lot. In fact, let's calculate the ratio. I mean, look. This is how much energy we had to pay for. We got this for free. That's pretty decent. In fact, that's how heat pumps work. They pull thermal energy from the atmosphere outside and put it in your home. So if someone tells you there's no such thing as free energy, you tell them, yeah, there is. It depends on what you need and where you look for it. Because you can actually get free energy. Energy is all around us. You just have to know where to pick it up. There's some practical places to pick it up and some impractical places to pick it up. Hopefully this course helps clarify those two a little bit.